Good morning. I'd like to start the notes again today on slide number 57, where we left off with this table of three-dimensional molecular structures that we can predict using the VESPR model. For a moment, I wanted to talk about why. Why are we doing this? Really, it's because we're trying to use these 3D shapes to help us predict the molecule's polarity. And that can be a tough thing. It's not always easy to know if a molecule is polar. I mean, we can try to dissolve it in another polar substance like water, but we're not always able to do that, and it may not be safe. And the way that we're going to do it theoretically on paper is twofold. One, we'll look at the electronegativity difference in each bond, right? And that's where we left off on our last quiz. We were able to find a bond's electronegativity difference and use a little arrow to annotate that. And then two, what we're adding to it now is we want to use the geometry of the molecule, which wasn't always clear, but VESPR helps to give us the best possible prediction of what that molecule's shape will be. And now we'll be able to see when two bonds really do cancel one another out, or when their pulls accumulate to a net polar end of the molecule itself. So that's kind of our hope. All right, so let's move on to our first slide for today. Just as a reminder here, electron geometry is not the same as molecular geometry. All right, so when we're looking at the electrons, that means we're looking at all the regions, bonding and non-bonding electrons around that central atom. And when we're looking at only the molecule, it means we're limiting our view to the regions of bonding electrons and the atoms that are sharing in that bond. And here's some basic examples. We're seeing water here in this image under A. And the electron geometry for water has the two lone pairs and then the two hydrogen atoms. And I just put EG for electron geometry. And then here, just the two hydrogen atoms around the central oxygen. So I put MG for molecular geometry, just to show that the difference. We've identified it as tetrahedral for the EG and bent for the MG, the molecular structure or geometry. Here's another. NH3, it's electron geometry, it's molecular geometry. Now the electron geometry is still tetrahedral, it looks like water did. But when we remove that lone pair, what we have is trigonal pyramidal. And how would we know that? Again, we're going to look back at that table and practice using that VESPR table to make these predictions. So it's not really something we need to memorize. But hopefully we'll get familiar looking at them. So step one with our VESPR theory is to make the Lewis structures. So I did that over here, Lewis structures on the right. And so the first one is CH4. How many pairs of bonding electrons? And again, this says pairs, so that's a 4, right? 4 pairs, not how many electrons. And then how many lone pairs? None. No lone pairs. Okay, so that is a tetrahedral structure. How about the next one? NH3, it has 3 pairs of bonding electrons. 1 pair, right? Again, 1 pair, not how many individual electrons. Non-bonding. So while its electron geometry is tetrahedral, this asks for the molecular structure, and that's trigonal pyramidal. How about water? 2 hydrogens, 2 non-bonding pairs. The electron geometry was tetrahedral, the molecular geometry is bent, and you can look that up in the table. Let's move on down to some less familiar ones. We have PCl5. So that is 5 shared pairs, no unshared pairs. And what kind of geometry has that? Again, when you look back up in the table, you'll find that it is trigonal bipyramidal. How about SF4? So it has 4 non-bonding pairs. I needed to make a Lewis structure to see there's actually 1 lone pair. So that's 5 regions of electrons. Just kind of looking at this Lewis structure, there's a lone pair right there. And so its electron geometry is trigonal bipyramidal, just like the previous one. I would need to look at the table to see that what remains when we look only at the atoms in the molecule is a seesaw shape. ICl3, so that has 3 bonding pairs, 2 I found out when I made the Lewis structure. Can I show you my effort to make a Lewis structure here? I hope that my artistry is getting a little bit better. So the basic Lewis structure here is totally fine. I've got my 2 non-bonding pairs, or trying to be better at depicting and getting my thoughts, my ideas together. I tried to make the non-bonding pairs oppose one another and then show the 3 chlorines on a plane more symmetrically. And in doing so, I can see that that shape a little bit better. Looks like a bipyramidal, like a pyramid on top and the pyramid on bottom. So it was trigonal bipyramidal before, with just the electrons being considered. But once we take them away, it's actually going to be a T structure. And again, I looked that up in the table. It may not have been as obvious, because one thing that happens is the non-bonding pairs do take up more space than the atoms with the bonding electrons. So they can kind of distort the shape of the molecule. And the shape of the molecule is something that we need the VESPR data to help us predict as accurately as possible. So the T structure is the result. And then finally, xenon, it has 2 chlorines around it, and I found out it actually has 3 non-bonding pairs of electrons because I drew the Lewis structure. And you can see 1, 2, 3 non-bonding pairs. I took that same Lewis structure and then I said, or I could just flip it on its side. Still, the 3 non-bonding pairs are in the same plane, and the chlorines are just now on the y-axis rather than the x. That's exactly the same. I just tried to give it a different perspective. And you can see right away that the atoms that remain are very linear. And so our structure overall is linear when we consider just the molecule. We have a couple more here. SCl6, so that's 6 bonding pairs, 0 non-bonding pairs. That is an octahedral shape. And I drew the Lewis structure over here. Lewis structures, okay. IF5, so we've got 5 bonding pairs, 1 non-bonding pair. And you're going to be practicing this on the homework if you haven't. You'll continue to. And I hope it's starting to kind of click now. When I drew it out, I could see a non-bonding pair of electrons here on the top. Looking at the table, that's what's left behind is square pyramidal. This one's actually kind of beautiful to me. Take a look at that square planar. When I draw it really nicely, I can see a square plane and then the pyramid at the bottom. So it's kind of fun when you draw it nicely and then the VESPR structure just jumps out at you. How about the next one? We have 4 and 2. And if I make an effort to try to make it as symmetrical as possible, it kind of starts to jump out at me. This is square planar. You see that square plane around it? And my 2 non-bonding pairs in there? Let's do a couple more slides here. So lone pairs of electrons take up slightly more space than bonding pairs. And they tend to compress the angles between the bonding pairs. So let's look at this diagram where we can see that. X is supposed to be, I believe, the central atom, and then hydrogen is some other atom. So these electrons in this cloud look like they're being shared pretty equally. But if X has a non-bonding pair surrounding it, both of those electrons individually are trying to get as close to that nucleus as possible. And so they sort of suppress this angle. And so they kind of take up more room. So the angle that they produce is broader. And at the bottom, I put both electrons need to be close to the nucleus. So they really do change and sort of distort the bond angle. Let's see some examples here. So the number of lone pairs here will affect the bond angle. There are no lone pairs on methane, CH4. So the tetrahedral is exactly as we would expect, 109.5. But ammonia has one non-bonding pair, so it pushes down on these remaining bonds, and what's there as a result is 107. Even with water, we see 104. Now, how can we kind of deal with that? We want to try to minimize the repulsion. Remember, that was part of the steps in predicting our proper VESPR model. So in predicting the structure of I3 here, there are different ways to arrange the lone pairs, right? In the first example here, we could put them all on the left where these gray clouds are, put a lone pair here, one here, and one here. Or we could put them all on kind of two on the central plane, it looks like, and then one on the y-axis. Okay, we're just comparing these three options to figure out which one looks the best, and then 2, 2, and 2. Well, since we know that lone pairs take up the greatest amount of space, then they're more likely to be on this central plane than they are to be on the y-axis plane. You see that y-axis plane had a 90-degree angle, and the central plane has a greater angle. So that actually takes us back to like 2 slides up where we had that T structure as a result. And maybe we didn't understand why at the time, but now we know those lone pairs, they need to be really on the central axis if possible, because that's where they get the greatest range to be able to minimize repulsions. The correct structure maximizes the distance, which means this is the correct structure. This is the most ideal structure for those lone pairs. Let's see another one. In predicting the structure of XEF4, there's different ways to arrange the lone pairs. The first way leads to a seesaw, and the second way leads to 4 on the same plane. So is it best to have the lone pairs 90 degrees from one another, or the lone pairs 180 degrees from one another? So clearly we want to have them as far apart as possible. So this is the most correct prediction for the 3D structure of this molecule, maximizing the distance between those lone pairs. And I want to point out that multiple bonds are treated just like single bonds in the electron pair arrangement. They do not change the structure of the molecule. The bond angle is still going to be as the model predicted. You can see up in that table, there's no special allowances made for the fact that there's a double or the fact that there's a triple. It really is how many regions are surrounding the center. We're going to stop there for today, and please update your notes, bring any questions you have to our next video session, or feel free to email me if you have some pressing questions before then.